Hello, pre-calc scholars. Yesterday we worked on finite geometric series. Today we're going to work on infinite geometric series. And we're actually going to call this 1.6. Originally I had hoped we could do these both on the same day, but since we didn't, I'm going to renumber the notes we're doing today to be 1.6. So in your packet, this is where we left off. Up until now, we've been finding sums for a finite number of terms. So that's a specific number, like 100, or 1,000, or 10 million. Now we're looking at what if there aren't a finite number of terms and the terms just go on forever and ever and ever. So our summation formula before was a sub 1 times 1 minus r to the n over 1 minus r. Now, I'm going to put some numbers in here. These can be random numbers. So let's say our original is 10. That's a sub 1. And then we add 1 minus 2 to the n over 1 minus 2. What do you think happens when n goes to infinity? So if we replace this with infinity, so if 2 to a power, that power just kept getting bigger and bigger and bigger, and we're adding terms forever and ever and ever. Well, eventually, this on top becomes a really large number. It essentially becomes infinity. This becomes so large that it's a negative infinity. And on bottom we have a negative 1. So these aren't truly equal because infinity isn't a number, but this is essentially what's happening. If we keep adding terms forever, the sum is going to get bigger and bigger and bigger forever. Now, that is if we have a series that's growing, right? It's going to give us this exponential pattern where it goes up and up and up and keeps growing more and more rapidly. Let me redraw that. So it's going to start slow and grow more and more rapidly. That's if our R value is greater than 1. That's what we chose, a 2. That's greater than 1. The case might be different if our series looks like this. If it's getting smaller and smaller and smaller, well, the sum might not go to infinity anymore. It might actually go to a specific number. So we're going to take a little bit of a closer look at that. So we're going to go to the next page, and then we'll come back to these examples. So here we have an infinite series because it just shows a dot, dot, dot. That means you're adding terms forever and ever. There's no end to the series. So let's turn these numbers into actual decimals here instead of fractions. So our first term would be 0.5. And then this is the sum of the first and the second. So it's the 1/2 plus 1/4. So that becomes 0.75. And then you add the third term, and then we get 0.875. And then 0.9375. I know this is tight. This table is really small. And then 0.96875. So we just keep adding. This last one here, S sub 6, is 0.984375. So these numbers are getting bigger, but the amount they're increasing by each time is getting smaller and smaller. And that's because our terms are getting smaller, right? 1/4 is smaller than 1/2, and 1/8 is smaller than 1/4. So we're adding less and less to our sum each time. And it turns out this sum is actually approaching a specific number. Can you guess what it is? It's 1. So our sum, let's say we're adding an infinite number of terms, the sum here is 1. It's going to get infinitely close to 1, essentially becoming 1. Okay, let's take a look at the next series. So it starts with a 1/2, so the sum is 0.5, then I add 1, so 1.5, and then I add 2, so 3.5, and then I add 4, so 7.5, and I add 8, which is 15.5. This is 31.5. Okay, so these numbers keep getting bigger and bigger. I'm adding more each time. 1 is bigger than 1/2, 2 is bigger than 1, 4 is bigger than 2. These terms keep growing. So this summation is not headed towards a number. It's actually not equal to anything. It's just headed to infinity. It's going to become infinitely large. So this is where it's headed. I'm using an arrow because you can't equal infinity, but it's headed towards infinity overall as you keep adding terms. So what's the difference between these two? The one on the left, we say that it's a convergent series. As we add terms, the sum is converging towards a single number. In this case, it was converging towards 1. The one on the right is a divergent series. It means that it doesn't have a specific sum as you add an infinite number of terms. It's either going to infinity or negative infinity. So what was different about these two series? Well, the one on the left, we said the terms kept getting smaller, right? So each time we're adding less and less. The way you make your terms become smaller is by having an R value that's less than 1. So you're multiplying by something like 1/2 or 1/3 or 1/4. So we want to say, that R is less than 1, and actually, specifically, the absolute value of R is less than 1. If the absolute value of R is less than 1, the series is convergent. It will come to a single sum. If, let's take this color, if the absolute value of R is greater than 1, so your terms keep getting bigger and bigger and bigger, then it's going to be divergent. And in the example above, we just estimated or looked at the pattern to figure out what the series was converging towards, which was 1. There actually is a formula that you can use to solve for the convergent infinite series. And that formula is S. You could write a little infinity sign here, but best practice is to just write a capital S. If there's no number underneath it, it means it's an infinite series. So S is equal to, A sub 1 times 1 over 1 minus R. So this is really similar to the finite geometric series. We just have a different numerator here. Instead of 1 minus R to the n, it's just a 1 in the numerator. Okay, so let's look at some examples. It says determine if this series is convergent or divergent. If convergent, find the sum. So first we want to figure out what our R value is, and I can tell that R is 1/4. 1 times 1/4 gives me a fourth, 1/4 times 1/4 gives me 1/16, etc. That R value is less than 1. So this series is convergent. I'm just going to put a C for convergent. That means that we're going to use the formula. Our initial value, A sub 1, was 1. And then we're multiplying by 1 over 1 minus R, which is 1/4. Okay, if we're simplifying, this becomes 1 over 3 over 4. We know dividing by a fraction is the same thing as multiplying by the reciprocal. So this becomes 4/3. Okay, now obviously I took up a lot of space there. I'm going to go back and erase some of this so that there's room for work on 10. So this comes out to be 4/3. So if we sum this series an infinite number of times, right, if we're going towards n is going towards infinity, the sum will converge to 4/3. Okay, now let's look at 10. To go from 2/3 to 8/3, I need to multiply by 4. From 8/3 to 32/3, again, multiply by 4. Okay, so R is greater, the absolute value of R is greater than 1. Therefore, those 3 dots mean therefore, we can say the series is divergent. And I ran out of space. We could also write a shortcut essentially and write D for divergent. Okay, so you get the idea from 9 and 10. Now let's take a look at 13 and 14. When this is in summation notation, it's actually even easier to notice if the series is converging or diverging, because the summation notation gives us R. The absolute value of R here is less than 1. Therefore, the series converges. And we want to find what that sum is. So S is equal to our initial value, negative 2, times 1 minus the R value to the, oh, nope, I was using our finite formula. Let's go back. So, if you remember, this is the formula we're using for infinite series. So this should just be 1 over 1 minus R, and R is 1/4. So this becomes negative 2 over 3/4. Again, dividing by a fraction is the same as multiplying by the reciprocal. So we get negative 2 times 4 over 3, which is negative 8 over 3. It's a little off the screen. So negative 8 over 3 for 13. Alright, so that's how you determine whether an infinite geometric series converges or diverges. And if it does converge, then you're going to use this summation formula. Again, this only works for an infinite series. If you have a finite series, you're using the formulas we've learned previously. Okay, we're going to look at another example here because all of our R values so far have been positive. Let's take a look at 16. Our R value on 16 is negative 3 over 4. That means the absolute value of R is less than 1. Therefore, this is convergent. And then we can use the summation formula. I've sort of run out of space here, so I'm going to do it just above. Okay, so we have S sub infinity, or like I said, just a capital S equals... Alright, now here we got to be careful because this starts at k equals 2. So my initial value isn't going to be negative 6. So if my A1 is negative 6, and I go from A1 to A2, by this R value, that means that I need to multiply by negative 3/4 to get A2. So negative 6 times negative 3 over 4 gives us 9 over 4 as our A2. So in this initial spot where I would normally put A1, I'm actually going to put A2 because that's our first term in this series. So 9 over 4. And then we have 1 over 1 minus R. Our R value is negative 3 over 4. So if you want, you can change this to a plus. You're going to plug that into your calculator or work on it mentally, and you end up with 18 over 7. So the infinite sum goes to 18 over 7. Okay, so let's go back a page. This part where we said go to next page and then return here. Example 17 says find the sum if it exists. If it does not exist, explain why. We can tell that they're asking for an infinite sum because of the ... And then we can look at this, find an R value. Each time we're multiplying by 1/3. Okay, so I know it's geometric. And I know that it's possible to find an infinite geometric sum. So I would say, since the absolute value of R, actually let me back up, since R equals 1/3, and the absolute value of R is less than 1, the series converges and the sum exists. That's all you have to say. in terms of an explanation, and then we would find the sum using our formula. I'm not going to show, we'll just show the general formula. The infinite sum equals a1, which is 36, times 1 over 1 minus r. So that's how we find the sum. Okay, let's look, well, before we look at the next problem, if this had given us an r value greater than 1, we would say since r equals whatever the r value is, let's say 2, and the absolute value of r is greater than 1, the series diverges and the sum does not exist. Okay, let's look at 18 now. It's a pretty different problem. It says use an infinite sum formula to write the repeating decimal as a fraction. So this bar over the 2 means that it's a repeating 2 forever and ever. So it looks like 0.2222222, right, going on forever and ever. We can break this up into 0.2, or that's 2/10, and then 0 and 2/100, and then 2/1000. I'm going to erase the work here so I have a little more room to work. And then 2/10,000, right? This pattern continues on. So the question is, how do we go from here to here? Well, you multiply by 1/10, or 0.1. To go from 2/100 to 2/1000, you multiply by 1/10, or 0.1. So each time we're multiplying by 0.1. That means my r value is 1/10, or 0.1. My initial value is this 2/10. And since this goes on forever and ever, we know it's an infinite series. We have to keep adding these additional decimal places. We can use the summation formula. I'm going to erase 17, so I've got a little more space to work here. Okay, so the infinite sum in number 18 is equal to our first term, which is 0.2, times 1 over 1 minus r, which is 1/10. So this becomes 2/10 divided by 9/10, simplifies to 2 over 9. So this series converges to 2 over 9. Okay. Example 19 is similar. This time, though, instead of repeating a single number, it's a pair of numbers. So this looks like 8, 7, 8, 7, 8, 7. And if we were to split that up, it looks like 0.87 plus 0.0087 plus, and then instead of 2 zeros, we actually need 4 zeros this time, and then 8, 7. And the pattern continues. You're moving 2 decimal places each time. So to go from 87/100 to 87/10, we have to multiply by 100th. And you can test this on the calculator, right? This shows that we're moving 2 decimal places, as opposed to 18, where we were just multiplying by 0.1 or 1/10, which moved at 1 decimal place. So the sum in 19 is our first value, which is 0.87 times 1 over 1 minus 100th. And if we were to plug that in, we would get 87 over 99. So that is how you write an infinite sum formula to write a repeating decimal as a fraction. So next, you should work on 1 and 2 with your partner, and after that, you're ready for the homework.